All right, it's 11 o'clock Mountain Time. So let's go ahead and get started. All right, got John with us here. Okay, thanks everybody for joining us today. My name is Brian Fox. I'm a senior applications engineer here at Flow3D. I'll be one of the presenters today. I'm also presenting with my colleague here, John Bouchard. Super excited to have everybody join us. We've got some really great case studies and really interesting content to present today. So first, just a little bit about myself. Like I said, I'm a senior applications engineer here with Flow3D. I've been doing CFD for about 15 years now. Come from a background in civil hydraulics, doing 1D and 2D modeling before getting into full 3D modeling. So really love presenting kind of the fundamentals and the introduction to CFD because that's precisely the background that I came from maybe 15 years or so ago. And then John, you want to go ahead and introduce yourself too?
Yeah, sure. Hi, everyone. My name is John Bouchard. I'm a senior CFD engineer here at Flow Science. My background is in mechanical engineering with professional experience with various 3D engineering software. I focus on water application like conveyance, water treatment, coastal, and my hobby is CFD post-processing and visualization. So thanks for joining us today.
So all the really fancy videos that you see today, those are all done by John. Well, good. Well, let's go ahead and get started. So the main goal of today's webinar is really to provide everybody a broad overview of 3D CFD, its capabilities, and really introduce it to folks that are new to 3D modeling. We'll also be showing some really interesting case studies from several of our users today. So in that regard, we're going to start off with a section on exactly what is 3D CFD, how is this different from other types of maybe more familiar modeling tools like 1D and 2D. And then after that, we'll talk a little bit about Flow3D HYDRO. So this is the specific software that we develop here at Flow Science. We'll go through some of the key features and capabilities. And then after that, we'll show some examples for how Flow3D is used in practice. John's got some really great detailed case studies, one in dams and spillways and the other in the world of wastewater that we'll go through. And then we'll finish up with just a few notes on different ways to get started with Flow3D if you're interested in getting your hands on the software, learning more, and then we should have some time for Q&A. So speaking of Q&A, if you do have questions that come up during the presentation, there is a Q&A panel in the Zoom toolbar, so click on that, enter those questions. We've got Dan Gessler joining us. He's our global hydro water lead. He'll be answering those questions along with Karthik Ramaswamy, who's our director of sales. So yeah, definitely send those as they come along, and if we have time at the end, we'll talk about some of those live. So let's go ahead and get started with this first section. What is CFD? So, very simply, CFD or computational fluid dynamics, it's just a simulation tool. We're going to get a very accurate, detailed, and dynamic representation for how water, liquid, or flow is going to interact with its environment. And then from these simulation results, we can use them for a wide range of different types of purposes in regards to design and analysis. More formally, CFD is a numerical solution to the conservation of mass, momentum, and energy, or what we call the Navier-Stokes equations. And so how this works from a very high level is we're going to start with some digital representation, like a 3D CAD, or maybe a terrain from GIS. We can also deal with dynamic cells. We're going to import that into our software or any 3D CFD software. We're going to create a mesh. So we're going to break up the domain or the flow area into individual control volumes. And then on each control volume, we're going to solve force equals mass times acceleration for a fluid. That's going to give us the raw output of things like fluid pressures and velocities. And then from that, we can post-process it to extract information. And that's precisely what we're doing here, where we create all these amazing images and animations that we're going to see throughout today's presentation. But for folks coming from a 1D and 2D background, I do always really like to emphasize that 3D modeling is derived from the same set of governing equations. So all of these different modeling approaches are part of the same family. so to speak, except that within a 3D model, we're solving for all three components of momentum. So it doesn't have the same types of limiting assumptions like depth averaging or the hydrostatic assumption that you're going to have in a 1D and 2D modeling approach. And so because of that, we can use 3D modeling in a wider range of applications, specifically the types of things that we would traditionally go to a laboratory environment for. We can now use 3D models to directly simulate those types of things numerically. And so in that regard, that's why I really like to, consider 3D modeling like your virtual lab or your numerical flume, in that it's going to give you that same capability that you would typically only get through direct lab experiments. So as an example, here is just a very simple case of an OG weir. So there's going to be some very strong vertical flow accelerations. This was something that would traditionally be handled in a physical modeling study for, just predicting like simple flow capacity or extracting pressures on the crest. But in the case of a 3D CFD, we can now directly simulate how flow moves through that structure. And then from those model results, we can accurately predict things like discharge capacity, crest pressures, or other desired outputs. But now the key with 3D modeling is we have full flexibility to make any change that we want, right? So we directly define the geometry, and the solver is going to simulate how flow is going to move through that structure. So in this case, we just swapped out the CAD of the OG weir for different shaped hydraulic controls or weirs, and the solver is going to automatically simulate how flow moves through that, and we can compare the discharge capacity differences between all of those. So again, there's no tuning parameters. There are, like you would have in a 1D or 2D model, there's no discharge coefficient. This is, discharge through these weirs is going to be predicted directly from the 3D flow solution. Looking at this from a different way, comparing CFD and lab data, this was a project that was completed by our users at Verdantis and GEI for the Santiago Creek Dam. So I just wanted to show this because it's just a really amazing comparison of the fidelity and the type of detail that we can get from a CFD simulation when we're comparing it, directly to an analogous setup from a physical modeling study. This was actually one of our featured case studies in our last webinar. So if you're interested in digging in more details of this specific case, you can actually access those on our website. So just getting a recording of that webinar, which I linked there at the bottom. So kind of bringing this all together, how does 3D modeling fit within the big picture? So I really like to think about 3D modeling as kind of, one tool or one option within the engineer's toolbox. Other tools to analyze fluid behavior are going to be things like physical models, standard design manuals, 1D and 2D hydraulic models, and there's also obviously a number of other domain-specific hydraulic modeling tools out there. But in general, we're going to want to use any of these to maybe do one of two things, like predict something that hasn't happened, like design optimization or future performance, or maybe gain some insight into understanding some complex process, maybe some structures not performing as expected. And so all of these different options are going to have their own pros and cons, and any one of these might be the best choice given goals and objectives, the complexity, timelines. Certainly there's a large number of constraints out there. But situations where 3D modeling can be a really great choice. If you're looking for a higher accuracy alternative to 1D, 2D models or their standard design guidelines, obviously the flexibility of CFD to analyze any type of unique design constraint can provide a tremendous amount of value, help reduce design uncertainty. In a lot of cases, 3D modeling can just be faster, simpler, and easier than some of these other approaches where you're trying to adapt those in situations that they may not have been explicitly derived or intended for. It's also commonly used as a supplement to physical modeling. So in this case, we can use CFD for rapid testing and then final validation in the physical model. This can certainly help reduce cost, improve the schedule, eliminate things like scale effects. And then after that physical model gets deconstructed, the CFD model obviously persists. So we can go back and look at future modifications using the CFD simulation. And then last but certainly not least, we can create some really amazing videos and images for communication with stakeholders, the general public, or other folks involved in the project. But ultimately, I guess the main goal here is if we're choosing the best tool for any given job, that's going to equate to more successful projects, which I think is what ultimately we're after by looking at 3D modeling. Okay, so that's kind of the first section on what exactly is 3D CFD. So now let's switch gears a little bit and talk about Flow3D Hydro. So Flow3D Hydro is the culmination of about 45 years of development of a general purpose 3D CFD solver. So the origins of Flow3D go all the way back in the 1960s at Los Alamos National Labs. The first commercial version of Flow3D came out in the early 80s, and then we've been continuously developing it ever since, right? So, throughout this whole time, our specialization has been on complex free surface flows. We've got users across all different disciplines of engineering, casting, aerospace, manufacturing. Flow3D Hydro is a application-specific version built specifically for civil hydraulics use cases. And so that's where we're at today. So to summarize some of the key technical features, obviously the core of what we're doing is our free surface modeling capabilities with called the volume of fluid method. So all of these simulations here are examples of what I call basic free surface simulation, where we've got some solid geometry or domain, and we're simulating how water is going to move through that. So the model setup and solver approach for all of these simulations is going to be nearly identical. These are obviously very complex hydraulically, but in the context of the model setup and the Flow3D simulation, they're quite simple, and in some cases even routine, right? So these are all very common things that people are using Flow3D for on a daily basis. Then we also have a range of different multi-physics modules. So these are additional physics that can be activated, and they're going to couple with the 3D hydraulic solver. So you can think of something like our 3D mobile bed sediment transport model, where we can define a mobile bed boundary and see how that bed erodes based on the applied shear stress from the hydraulic solution. We've got our DM or particle model here. So we've got full 3D particle interactions with our new DM model, air entrainment, moving objects, also a mine tailings or debris flow, which allows us to define non-Newtonian flow properties based on a local sediment concentration, and along with a slew of other physical modeling options. But again, these are additional components that couple with a 3D hydraulic solver. Then we have a fully integrated GUI for all of our model setup options. This can make for fast, simple model setup and post-processing. A big part of our product offering is our engineering support. So this is going to include all of our training options. So we have on-site and online options. It's a picture of our 3-day training at our offices in Chapel Hill, North Carolina. We also provide live tech support with all of our licenses. So if you ever have problems or need help, you just call us. We can set up student chats just like this one to help work through whatever you need to be successful. And then we're also working on the development of application guidance and best practices, something that has been a big focus this year and continue to be into the future. We're also extremely involved in the community. Members in all of these organizations you see here. We regularly attend industry conferences like ASTSO, USSD, and EWRI. And we actually just hosted our own users meeting and symposium here in Denver last month. So it's 2.5 days of presentations from Flow Science staff and users, lots of advanced training and discussions. But really great participation from our users in private industry, government, and academia. If you're interested in browsing some of the topics from this symposium, you can check out the proceedings at that link up at the top of the screen there. Okay, so that kind of wraps up this first introductory section. Now let's get in kind of the main part of today's presentation with some case studies and examples. Okay. I guess first, just we'll take a high level look at the range of different ways that Flow3D is used in practice through each of our five major application areas. It's going to include dams and spillways, conveyance infrastructure, river environmental, water treatment, and ports and coastal. So I'm just going to give a broad survey and talk about what our typical applications are in these areas. And then I'm going to pass it over to John, and he's going to dig into the details of two specific case studies, one in the world of dams and spillways done by our users at Hazen and Sawyer, and then one for water treatment from our users at Stantec. But first, just kind of going through all five of these, and again, talking about them from a high level. Dams and spillways is our oldest application area, probably one of the oldest ones for CFD and civil engineering. So common use cases are going to include things like spillway capacity through various types of hydraulic controls, stilling basin performance, fish passage, rock scour, among many other things, obviously. But really, because of the uniqueness and the complexity that you often see in these structures, I think the generality and the flexibility of a fully 3D solution is really going to be well suited to these types of applications. And so again, John's going to show a really great example in a few minutes and dig into the details of those. Then next we have conveyance infrastructure, which is also a major application in Flow3D HYDRO. It's going to be commonly used for the design analysis of stormwater, wastewater collection systems, things like CSO diversions, drop structures, pump stations. So it can be very similar to, in nature to dams and spillways. So, looking at flow capacity through small weirs and orifice controls. But now we're often dealing with, combined free surface and pressurized flow conditions, which is handled seamlessly with the solver. And then next we have river environmental applications. So this can encompass a broad range of different use cases for river hydraulics and sedimentation application areas. So smaller in-channel hydraulic structures, plumes, contaminant transport. We also have a combined 2D, 3D solver. So we can run a single simulation where we have a portion of the domain and 2D depth averaged flow, similar to HEC-RAS or any other shallow water solver. So we can do that for computational efficiency and then switch over to a fully 3D model around a structure, other part of the domain where we want to get more details or more accuracy in that region. But I think this is actually one of our fastest growing areas. I think traditionally there's a lot of smaller applications out there where perhaps people just really didn't consider using 3D modeling. But obviously with the advancements of solver capabilities and compute speed, a lot of these applications are pretty straightforward to do in a 3D modeling environment. Then moving on to the world of water and wastewater treatment processes. This one's quite a bit different from our previous applications. But first, in terms of core capabilities, it can be used for general modeling of treatment plant hydraulics, looking at flow splitting, flow splitting and flow capacity, head losses, potential short circuiting, pump station approach flows. But there's also some really interesting capabilities in regards to the advanced physics modeling for different types of treatment processes. So looking at disinfection with our reaction kinetics model, there's a lot of different ways to evaluate sedimentation, particle modeling. So lots of, again, really exciting opportunities there for CFD. And like I said, John's going to be showing a case study of a chlorine contact tank here in a few minutes. And then last, but certainly not least, we have ports and coastal. The big focus here is going to be wave structure interaction. So in this example, we've got artificial oyster reef where we're looking at wave transmission, but certainly other possible applications include things like prop wash, coastal outfalls, wave energy, and other types of maritime applications. Okay, so next we'll get into the case studies, but before we do that, we actually have a poll. So we're curious to find out which of these application areas most relates to what you all are doing. So if you want to maybe fill out that poll, we'll show the results here at the end. Okay, so I'm going to go ahead and stop sharing, and then John's going to take over, and we'll talk about some interesting case studies.
All right, can you see my screen? Can you hear me?
Yep, loud and clear.
That's good. It's really interesting to see how the poll is evolving. We have a lot of people doing dams and spillways. Second is river and environmental, followed by conveyance, then water treatment, ports and coastal. It's almost tied.
I think you can continue, John.
All right.
We'll come back to the poll results at the end.
All right. Well, dams and spillways seems to be the winner. It's a good thing because my first case study is in the field of dams. It's about using CFD for an innovative spillway design project. And my second case study will be in the world of water treatment with a contact tank improvement project. So let's start with our first case study, which comes from our users at Hazen. And it was actually presented at the last ASDSO conference in Cleveland by Ann Hausman and Ben Winter. It is showcasing the use of CFD modeling to a novel dam rehabilitation project. This dam that you see here is located in western North Carolina, and it is classified as a high hazard dam by the state dam safety program. And what's triggered this project was that the spillway did not meet the current regulation. So it needed to be updated to add more discharge capacity and be able to pass 100% of the probable maximum flood, or PMF. So on the top right, we have an overview of the area, and we can see where that existing dam and spillway is located. And we have now a close-up view of the existing dam. As with many such projects, there are conflicting sets of constraints. So of course, there's the regulation, but also site and budget constraints, as well as impact on the local residents. So since this is a scenic area, as you can see, and the spillway is discharging in a creek by a golf course, there was a concern for the footprint and aesthetic of the overall solution. So remember that they needed to add more discharge capacity. So when you have such a situation, the conventional thinking would be, well, let's build a larger straight spillway. And that's probably like the area that they would have considered to do that because of the space required by this type of structure. However, this would have been a major change to the landscape, and adding a new spillway also meant higher cost. So it was decided to explore spillway alternative at the existing location. Using CFD early in their project allowed them to evaluate these more complex design alternatives that would have been too risky to consider otherwise. Without CFD, they would probably have to play safe and stick with that long linear straight weir at the new location. However, if we look at the existing area, we can see that space is more limited, and also that the approach flow is less ideal because of that bend right here. And that bend is on the bedrock. So it would cost a lot of money to completely remove that mound. And also there was some concern because how a greater flow would behave downstream because it's running into a creek by this golf course. So here we see the different spillway iterations that were considered. As you can see, they originally started with a 90-degree bend to keep the existing bridge, but eventually they reduced that angle to improve the flow up to the final design. So here, what these different iterations look like in the CFD world. As I said, they originally started with that 90-degree bend because they wanted to keep that smaller bridge, or that existing bridge, in fact. But unfortunately, that created problematic approach flow losses. So they eventually reduced that angle to improve the flow up to the final design on the right. In addition to the approach flow conditions, they also considered the flow behavior in the spillway and downstream in the creek. And also, as you'll see later, the design is using fuse gates, which are meant to tip in sequence, going from right to left here in the event of a flood. A little bit of information about fuse gate. As you can see on the upper right, their final design combines a labyrinth weir for the service spillway with a lower crest height, and some fuse gates with a higher crest height that act basically as an emergency spillway and tipping in the event of a flood. So for your info, fuse gates is a concept that has been developed by a company called HYDRO, and they are designed to tip whenever the water surface elevation reaches a certain level. So their goal is to prevent damage to other surrounding structures like the embankment in the event of a flood. So they are basically the hydraulic equivalent to a fuse in an electric system, with the same goal of protecting the system in the event of a surcharge. So we can see here in this little animation on the lower right that when the water level reaches a certain height, the fuse gate will tip. But in normal operation, it acts as a nonlinear labyrinth or piano key weir. So, and as I said, in this project, the fuse gates were designed to tip in sequence based on water surface elevation. So they use CFD to test and optimize this innovative spillway design with a couple goals in mind. So first, as mentioned, trying to minimize the approach flow losses to optimize the discharge, but also making sure that the fuse gate will tip in sequence. Because since and here we see like an intake tower that actually prime those spillway, those fuse gates. And since this is based on water surface elevation, and as we can see here on this free surface elevation map, there's kind of a depression here near the spillway. So they needed to find a good area where water surface elevation would be stable to properly activate the fuse gates. And finally, another thing they made sure was that there was not too much submersion or back pressure effect. So that's what we see here. So this back pressure would actually prevent the gate from tipping. So they adjusted the seal height accordingly. So in summary, CFD allowed them to consider maybe less conventional design elements for this project. It gave them the flexibility to adapt their design to the complex set of constraints in order to make all the stakeholders happy. And at the end of the day, it enabled the development of a better design and also to gain confidence in that design, rather than playing safe with a more conventional straight weir at the detriment of cost and aesthetic. And as a bonus, CFD allows to create these nice visual assets, which are great for communicating and sharing information with the stakeholders. So they were kind enough to provide me with their simulation files, and I played to make some renders. Here we have like water receding, showing the streamlines. So this is all done with Flow3D Post based on their simulation. This is for one scenario where a couple of these fuse gates have tipped. And if we look at that opening video, here we have an overall view. Let me just take it back. An overall view of the site. As you can see, we can map satellite or drone imagery on top of the terrain. And we're zooming in to check out the approach flow conditions with the streamlines. And then taking a closer look at how the flow is behaving in the spillway. And we're just looking at with a cross section that is moving. and finally ending with an overview. So as I mentioned, this is just me playing with their data. It was all done in Flow3D Post, and the possibility are almost endless of what you can show in terms of data. So now let's move to our second and last case study. This one comes from Stantec UK and takes us to the field of water treatment. You might have seen our friend Victor Lira posting about it on LinkedIn lately. We found it really interesting, so we decided to include it in today's webinar. So this project was done for a UK utility company for one of their drinking water treatment plant. Just to provide a little bit of background, here we have a generic drinking water treatment process where water is first pumped from a river or a lake and then goes through a series of processes to remove particles and solid in preparation for the final stage before storage, which is disinfection. So in this case, we see the actual contact tank that they were dealing with. And in their case, their chlorine contact tank was underperforming. So we can kind of see the structure. It's a massive structure. You can see, get a sense of scale by looking at the picture, just so you understand water is coming from below and flowing through this maze to reach the outlet, and they inject chlorine to disinfect or keep that drinking water in good conditions. So very often when such a system is underperforming, the unfortunate consequence is a greater use of chemical, which of course is not good for operation costs, but also for the environment. So the goal of this project was first assessing the current conditions. Contact tanks are a little bit like black boxes. So CFD would be used or was used to understand and visualize the current flow pattern and performing a virtual tracer dye test. So inputting a tracer at the inlet, letting it flow and measuring the concentration at the outlet. And then they repeated the same set of simulations for various proposed modifications and check how that improved performance or not. The goal was to decrease short circuiting and dead zones. And intuitively, when you look at streamlines like this, you can see that there's a jet of water that is moving very efficiently, while there are some areas that are what some people call dead spots. So they used CFD to quantify those. Of course, this is an existing tank, so modifications needed to have a minimal impact on the structure. And also just have to keep in mind that these contact tanks operate in various flow or water surface elevation conditions. So the solution needed to work for all cases. So to illustrate the different scenario they considered, here we have the three designs. So the current design that you've seen previously, they also considered option A, where they're adding these three little walls, and option B, which is basically the same as option A, but with perforated walls. So for each of these designs, they evaluated three flow and depth conditions. So the maximum flow, minimum depth condition. No, sorry, this is the average one. The minimal flow, maximum water depth. So you can see a little change in water surface elevation. And finally, now the maximum flow, minimum water depth condition. So Flow3D is a transient solver that will simulate the evolution of the flow field over time. So the first step of their simulation or their project was to run the simulation until it reached steady state. And then when it reached steady state, they did a simulation restart. So you restart from that stage and they activated scalar physics. Let me just bring it back. So that's our virtual tracer dye test right here. So putting a dye or a tracer, which is Flow3D considered as a scalar, in the inlet. and then tracking how it's moving and measuring the concentration at the outlet in order to plot a residence curve. So more info on that later, but that's basically what you're seeing here on the right. So now let's look at some CFD result and see how the current tank configuration was performing. So these are results for the maximum flow, maximum flow rate, minimum water height condition, which is the most critical flow condition. But it's worth noting that the other conditions showed similar flow pattern. So just so you get a good understanding of what we're looking at here, so on the top left, we have a general view showing the 3D flow pattern using streamlines. These streamlines are colored by velocity. Now on the upper right, we have a 2D slice view of the same simulation seen from the top at mid-level, showing once again the velocity field using these little white vectors. And as you can see, we have this high velocity jet of water that is racing to the outlet. And on the lower right corner, we have another 2D section view where water this time is colored by water age, or residence time. So that allows us to see the stagnant zones or the dead zones in red. So those areas are like you don't have sufficient disinfection because water is still there, chlorine decays, and that's a problem. So now let's look at some hydraulic data metrics from their CFD analysis of the current situation or the current design, with the Qmax scenario highlighted in yellow. That's the one we just looked at in the slide before. So remember that they simulated injecting a scalar like a dye tracer at the inlet and measuring the concentration at the outlet. So that allowed them to generate a cumulative distribution curve, like here, also known as an F curve. And on the x-axis, we have the time in an hour. And on the y-axis, we have the ratio of the concentration of that tracer that reaches the outlet. So the slope and inflection of these curves are indicative of the performance of a contact tank. A steeper curve means that we're getting closer to an ideal plug flow. So for those who are not familiar with the term plug flow, in a plug flow scenario, if you release some dye at the inlet, then all of the dye arrives at the outlet at the same time. So that would be like having a vertical line here on that graph. Of course, in real life, that's not possible, but that's what we aim for. In real life, you have a portion of the dye that will arrive early, following that high-speed jet, and another portion of the dye that arrived later. So the farther that's spread, the farther we are from plug flow. So so we see that here with the current situation, the spread on the graph is not ideal. And on that table here on the right, we have some metrics from the same simulation. So without going too much into detail, basically all of those T5, T10, T50, T90, T95 are just ways of quantifying how that arrival time is stretched out. Then we have the baffling factor, which tell us how close we are to plug flow. So a plug flow would be a value of 1. But per the customer standard, a value above 0.7 is considered as a superior plug flow. And then finally, we have the Morrill index, which is an indication of the degree of dispersion. The lower the value, the better. So we can see how the current configuration in all operating scenarios mostly fails on all of these metrics. So let's bring back the current configuration simulation just to refresh your visual memory and to act as a basis for comparison. And now let's look at other options that they considered. So that's the kind of the before, and this is with option A, still with that maximum flow rate condition. We can see how remember they're adding little walls, and we can see how these walls are forcing a different flow pattern and getting rid of a lot of that short circuiting. However, we can see that there are some little dead zones forming behind them. Now let's look at option B, which is basically the same thing, but with perforated walls. Once again, we get rid of this short circuiting because we force a different flow. And we also remove portion of those dead zones because the walls are perforated. There are still some little dead zones, but nothing compared to the initial situation. So if we take a new look at the F curve, once again, the black curve is the existing. And here we have, it's probably a little bit hard to see, but option A and B are almost overlaid in blue and red. And we can see that their curve is much steeper, so we're closer to plug flow. And then if we look at the table, we see that everything that was in red with the current situation is pretty much now in green. So it was finally decided to go with option B, which is the option with perforated panels, since it showed a slightly better performance on all of these metrics and even getting, as you can see, a superior baffling factor. So they reach basically 0.7. Which is considered very good. So in summary, this was a great case study to illustrate how CFD allows us to see the flow that would otherwise be invisible in this type of structure. It allowed to test various designs and under certain operating conditions, and with the goal of improving the hydraulic efficiency. So that was achieved. They went from an average to a superior baffling factor. And all of that simply by adding 3 perforated panes. So that's quite a bargain for the results they were getting, especially considering that a more efficient tank requires less chemicals. So they're saving also on operation cost. So ROI is probably really good with that project. Plus, this is a more sustainable solution for the environment since you're not wasting chemicals. And so on the right, we can see a before and after. So I didn't start the video, but we see how on the video of the bottom, the dye is no longer rushing to the outlet, and we have overall a better, more uniform mixing. So doing this type of project without CFD would have required doing a bunch of trial and errors, draining the tank to make modification, refilling it, and so on. And you would also only be relying on probe measurements to measure chlorine concentration at discrete locations, rather than getting a full picture of the flow. So it's kind of like poking your way in a dark room versus turning the lights on. And the beauty is that this is really not a complicated simulation to set up. And so if you want to learn more about developing this kind of expertise and being able to run this type of simulation, Brian will share this information with you or in the upcoming slides. Thanks.
All right, so let me take back over here. Okay, everything look okay? Sharing successfully?
Yes, all good.
Good. All right, so for the rest of the time here, I'm just going to quickly kind of walk through what the model set process looks like, just so you can see what's involved there. And then we're going to finish up by discussing some of the training options that we have coming up in 2026. Right? So just quickly walking through the model setup process here, again, if you have experience in 2D modeling, the overall setup process is going to be pretty similar, right? So we're going to create a new simulation, but the key steps are going to be first creating your geometry. So as we talked about before, this could be importing a 3D solid object that you can create really in any type of 3D CAD software. But again, that imports as a closed STL. We can also import terrains from GIS and GeoTIFF format. We can import LandMXLs, which is a generalized TIN format. So if you have a surface object in Civil 3D, export that to a LandMXL. That comes directly into Flow 3D. You can combine all of these things. there's lots of flexibility for how we create geometry. After that, we'll create our computational mesh. So we use Cartesian meshes. So you're going to overlay this mesh onto the geometry, and the solver is going to automatically embed the geometry into the mesh. And so this is one area where I think CFD gets a reputation for being extremely intensive to set up. This process is really straightforward in Flow3D because of this combined geometry meshing step called favor. We'll get into that into our training classes, but I think it's a key aspect and a part of our model setup process. Then we'll define our boundary conditions. Again, this is going to be very similar to 1D and 2D model. We'll typically define a flow rate at an inlet. You can also define a fixed elevation or headwater. And then at the outlet, we can define subcritical, supercritical outflow conditions. For dealing with coastal applications, we have a variety of different wave boundary options and other kind of specialty boundary conditions for certain scenarios. And then after that, we'll run the model post-process. But what I just walked through is what I call our basic free surface simulation. And this can cover almost everything that you do. In terms of, time in the solver or time in the software, it can often be pretty trivial. And what you do next after setting this up and running it can vary greatly, just depending on the goals and objectives, what you're trying to do with the project. Are you doing multi-physics modeling? This is where our support services can come in handy because we can consult and advise on different ways to proceed as you progress your simulation. Okay, so if you're interested in learning more, I've got a few options for you. So maybe a good next step will be to attend what we call our discovery workshops. These are what I like to call our quick start introduction. And so there's an online and an on-site version. The online is a half day. The on-site version is going to be a full day. And so we've got on-site classes coming up in Houston, Texas, Kansas City, Missouri, Washington, D.C., and Sacramento, California. But in both of these classes, we'll give maybe a little bit more detailed introduction on CFD. We'll go through the whole model setup process. We work through several exercises, and then you get a full 30-day training and evaluation license where you can spend a whole month working with the software. You can work with one of our application engineers to test out one of your projects. Really great deal. So I think who would benefit most from this, if you're interested in using Flow3D for future use, obviously this is a great way to evaluate the software. If you're just looking to get a little bit more information, maybe your manager or stakeholder, you work with others who do 3D modeling, this is also a good way to get your hands on the software and just see a little bit more about what goes into developing a 3D model if you're interested in doing so. And then one last note is if you would like to attend any of these classes in 2026, we are offering 50% discount off registrations through the end of the year. So definitely get registered by December 31st to hold a spot and get a nice discount there. If you're looking for more in-depth training, we do have a full, what we call our 3-day comprehensive foundational training course. This is held in our offices in Chapel Hill, North Carolina, with the exception of one class coming up in June, which we're going to be hosting at a site in Denver. So again, this is a full comprehensive introduction to Flow3D. There's going to be a series of exercises, lectures, and guided discussions. So if you're a new or potential user and you want a full A to Z introduction, this is definitely the class that you want to get in. If you're an existing user and you're looking for a refresher on fundamentals, this would also be a fantastic course for you. And if you have a permanent license in maintenance, the registration fee is part of that software maintenance. So definitely take advantage of that. If you're an existing user, talk to your account rep and they can give you information on how to get signed up for that. If you're not ready for either of these classes and you're just interested in maybe a little bit more information, feel free to reach out to us at sales@flow3d.com. Happy to provide a consult on your specific project needs. Also happy to set up one-on-one lunch and learns with your engineering team. So if there's a specific application area you want to dig into a little bit more, or a specific capability like sediment transport that you want to learn more on, just let us know. We're happy to set up a lunch and learn for your group. Also happy to discuss software licensing options if you're looking for that information for planning purposes. Okay, so just to wrap everything up here today. So again, some of the big themes and take-home messages to leave with. First of all, just the benefit of 3D CFD modeling, as a tool to provide accuracy, flexibility, and versatility, help reduce risk and uncertainty. It's very complementary to other approaches, not just with physical modeling, but with 1D and 2D, and also as an effective communication tool. Again, we see all of these amazing images and animations. Again, just a really amazing way to communicate results that would be difficult to impossible to do otherwise. And then with Flow3D Hydro, again, we're industry-leading CFD modeling software for civil applications, streamlined, intuitive workflow, wide range of training content, technical support services for general engineering support, and commitment to the civil engineering industry. So we're constantly developing and improving our software based on user feedback to meet the needs of the industry. So that's all we have for today. I think we've got a few minutes left. Karthik, if we've got some questions.
Yeah, absolutely. Thanks a lot, John and Brian. I think really interesting webinar. The questions have been very interesting and keeping us all occupied for the last hour. I'm going to end the poll real quick because I'm sure, I don't know if I can share these results with everyone. But if not, we'll send out a quick survey. It's the same order as Jonathan mentioned. We have dams and spillways leading with 70%, rivers at 65, conveyance at 43, ports and coastal and water treatment around 20%. And thank you for sending in your details to the other tab as well. Oh, I can share results here. So maybe people can see this. Should be interesting. Excellent. Okay, so we do have a few questions. I think to start off, Brian and Jonathan, there were quite a few questions that came in about geometry. And I was wondering if you guys could give a short overview of how we handle geometry in Flow3D and what options are there to handle things like STLs versus bathymetry, for example.
Yeah, so obviously this can be, sometimes the biggest part of your project, and how you want to develop geometry can, first I think it comes down to the data that you have, how you're collecting it. Do you have terrain data that's in GIS as like result from like a LiDAR survey? Do you have a three-dimensional model already built? Like a lot of times people will have like a Revit project that came from the mechanical or the structural team. So I would first look at, okay, what data sources do I already have and what am I trying to do? Doing a full 3D solid geometry, that's probably the most general way to develop. I mean, you could do anything with that. And so that can be the most general way to develop a geometry. Sometimes it's a little cumbersome if it's a large area. So that's where we might want to look at things like rasters or 10 objects to cover a large spatial area. So a lot of times it might be a combination of these things where you're using an STL for a small detail of the structure, and then you might have a raster of the approach flow conditions. But the solver is set up to accept all of those inputs, and we're going to automatically kind of Boolean these things together. So, you have the flexibility to maybe switch out the STLs, put in a new terrain, but it's all kind of like a building block approach where we can combine them together, right?
Excellent. Yeah, thanks. Yeah, I think also to speak to that, the ability to do 2D, 3D shallow water models, having the flexibility in geometry can be really, really useful.
Yes, just to kind of talk about that, I didn't really get a chance to talk a whole lot about our 2D, 3D modeling capabilities, but I think that's a huge component of what we can do in Flow3D. So, a lot of times I'll have a model, and let me just run like a quick 2D shallow water model to see where water is moving, set up my initial conditions, drop a 3D mesh block around a small area. And so the reason that we do that is with a 2D model, you have essentially one cell in the vertical dimension. And so it's just faster to run these things, right? So if the assumptions are valid, so if it's a good assumption, hydrostatic flow for a 2D model, let's certainly take advantage of that in terms of runtime, and then switch over to a 3D mesh block to get the full 3D flow effects, maybe like around like a bridge pier or some other structure, a bend in a river where we have these recirculating flows, are all good cases for this 2D, 3D hybrid.
Absolutely. Excellent. Thank you. This next question comes from Olivier Tremblay, who we know well. This is for John Bouchard. Mapping a satellite image on the terrain in post seems to be a very interesting feature. Is the procedure complicated?
Yeah, no, it's actually not that hard. It's very simple if your terrain data and imagery comes from, let's say, a GIS platform, and you have the exact same cropping for both. So this is really straightforward. You do that in Flow3D Post. There's a filter to activate the texture and map it on your data. It's a little bit more tricky when both the data and image come from different sources. And the only tricky part really is to have the same cropping, and you need some time to fine tune the alignment in Flow3D Post. But yeah, all in all, that's pretty straightforward, and it makes for very nice videos and like assets to share with the stakeholders.
Absolutely. And you've done a few of these now, right?
Yeah.
Yep. Yeah, we see that being used more and more. People love this.
One note on development, we are moving towards formal handling of like spatial coordinate systems, which is going to give us the capability to directly integrate things like aerial photos and more seamlessly allow that overlay. So that can't make any promises which version, but that type of capability should be coming in the future.
Yeah, absolutely. It's a very, very good point. Here's a slightly different question from Spiros Mikas. How can we assess hardware requirements for simulations and visualizations? Do you guys have any notes or things to speak about as far as hardware and scaling goes?
So that's a great question. So usually when people ask that, there's a really great article by our IT manager on picking out a machine for Flow3D. I don't know, Karthik, if you've got that link,
yeah, I'm going to post both the recommended and minimal configuration and that article that you're talking about, Brian.
Yeah. So in short, the processor is going to be kind of the king in terms of what's going to be important for speed. So the number of cores, the clock speed are obviously important. But what really kind of drives what you're going to need is you figure out, all right, what are you actually simulating? How many cells are going to be in your simulation? Like if you're running pretty small simulations, like you don't really need a high power computer. You can get things done really quick without it. And not only do you not need it, it could even slow your simulation down in some cases. But so if you're running large cell count simulations, like in the order of 10, 20, 30 million, that's where you want to start looking at these high core CPUs, high clock speeds. RAM is less important. The graphics, currently we're not doing any GPU acceleration, so we don't need GPUs for the computation. So you can get away with relatively minimal graphics cards for display, but really the processor and also picking out a RAM configuration to match the processor is maybe another important aspect. But I would recommend checking out that article first. And if you have specific questions, let us know. We regularly review computer specs for users before they purchase it and make recommendations to optimize the runtime for Flow3D. So
I put the link in the chat.
Awesome. Thanks, John and Brian. Yes. As Brian mentioned, I think it's important if people have specific configurations, especially with hardware becoming cheaper, we're more than happy to take a look and give you guys some feedback. We don't sell hardware ourselves, but we can take a look at it and advise on this. Okay, it looks like we're just about at time, so maybe this is a good place to go ahead and wrap it up. I know there are still questions in the chat. If you have sent a question in and have not received an answer, we've done our best to answer all of them, but don't worry, we'll get back to you. We have your info if you've shared your info with us for the question. Otherwise, you have John Bouchard's and Brian Fox's emails here on screen. Feel free to reach out to them directly with anything you have. But thanks very much for joining us from wherever you are, and we'll we'll go ahead and close out this webinar. Thank you, John and Brian.
Thank you.
Bye. Thanks.